Okay, Santoshi, I think now it says connected to YouTube.
Connected to YouTube.
It's already there. Let me just check the link. Playback on other websites has been disabled by the video owner. Watch on YouTube. Shall I click on watch on YouTube?
Yeah, you'll have to click on watch on YouTube.
Okay, so I can see.
It'll stream in 10 to 15 seconds.
Now every time will the link be same or it will be
It'll be the
different?
same for everyone.
No, I mean right now whatever session is happening that is coming on one YouTube Remo presentation. Next afternoon when we click, will it again go to the same YouTube link?
Yes, because yeah, we've used your account. For your account, we sent off the direct Remo link, so it'll be one link only.
Okay, fine. Thank you. I'll just paste this in the chat so that people can. I'll paste both the links, the first one and the second one.
Sure. All
Yeah,
right.
yeah. Thank you. We'll just resume in another 5 minutes. All the participants can take a short break. Another 7 minutes. We'll resume. Thank you. Yeah.
All
Now
right.
the YouTube link is live. So when we came back to this, we had to click on that one checkbox. That has been done now.
Okay.
And again, we have to make everyone as presenters. So I have Ashokan sir, Professor Venture, Professor Harada, Professor Saha, Professor Shibata on stage.
Okay. Okay, who else is to come?
Uh, Professor Ekta Singla, I don't see her online.
Okay.
Checking my screen, my presentation.
Yeah, but the audio will not come, sir. You may have to
Why?
speak when this is the technology, I mean,
Acha,
the
okay.
portal problem.
Okay. But just check whether this is shared or not already.
I'll have to stop sharing. Please do it. Yes.
Let's check the video, or at least video works or not.
Yes, we can see the video, but the
Okay. Oh, fine.
sound you may have to speak.
Okay, no problem.
Okay, other speakers, if
Shall
you want
I,
to test. Yes, sir.
discontinue?
Yes, sir. Please stop sharing. Right side below. Yeah, somewhere there. Share that one. Yes.
Rajiv, I will check my slides.
Yes, sir.
Should I do entire screen or only the slide?
Anything is fine, sir.
So it's visible?
Yes.
Yeah. So on stage we have Tom is there. Professor Harada is there. Professor Yamazaki is not there.
Yeah, I think he has left.
Left? Has he left?
Yes, I don't see him.
Yeah, I think he has left. Then Professor John Shore is there. Then from the India side, Subir Saha is there. Ashokan is there.
I'll
Ekta
just
Singla.
message Ekta ma'am. I'll just check with her.
Okay, that's fine. So,
I think we can start.
yeah, Ekta wants to check, she can do that.
Yeah, so it's 10:55, so I think we can start.
Ashish, your voice is a little bit low compared to others. Maybe, I don't know, only for me or for others also.
Okay, good afternoon and welcome again. So the second part of the workshop, we have the talks from the India side. So we have 4 speakers from India side. Professor Shubir Kumar Saha from IIT Delhi. Professor Ashokan T from IIT Madras. Professor Ekta Singla from IIT Ropar and myself Ashish Datta from IIT Kanpur. So we start off with Professor Shubir Saha. So please keep your talk to within 20 minutes. Yeah, Professor Saha.
Yeah. So good morning and good afternoon. Konnichiwa minasan. So this is a nice opportunity to meet many of the Japanese colleagues as well. Particularly, I remember 2010 when I met Professor Shibata with the request from Professor Ashish Datta to initiate a dialogue of the Robotics Society in India, and now where we are. Thanks for the continued support from the Robotics Society of Japan. So the title of my talk today is Arts Robotics, Robotics to Robotics actually. I'll tell you why it is like this at IIT Delhi. So I'm professor at the Department of Mechanical Engineering and acting as a project director of a new non-profit company at IIT Delhi. And on the right hand side, the logo, we are celebrating 68 years. So to begin with my experience, as has been directed by Professor Datta, is to talk about robotics at IIT Delhi. So my experience with robotics at IIT is from 2001 when I started the mechatronics laboratory here. I just wanted to show you a device, a simulator which we have done as a truck simulator for our Indian Army. So this manipulator, the motion platform, which is basically a sphere platform, is a very popular device used as a flight simulators. But here the target was a truck simulator. So complete kinematics, dynamics, motion planning was done at IIT Delhi. Later on, it was taken to the site in Hyderabad, which is kind of south of India, and we did the integration there. When we were developing that truck simulator, which was about 1 ton payload capacity, we are also playing with these kinematics to understand the control and other aspects. So we developed a small device for which we later found an application by our professor in biomedical engineering for etching implants. So you can see how the laser spot has to be traced along the implant. So a nice offshoot application, and now this is so cute and so useful for the education. We are making it available for the other researchers outside IIT Delhi as well. Then comes 2010. We had a sponsor program from our Atomic Research Center at Mumbai, and we created a program called Program for Autonomous Robotics, and that was another program which was led by Professor Shantanu Chaudhary, whom you met in the morning. He was a faculty at IIT Delhi, and he was leading this activity where about 12 faculty and 20 students were taking part here. And we have developed several technologies. I will show you maybe 1 or 2 glimpses here. And as a part of our annual workshops, we also planned the Robotics Society that time onward. So we are very obliged to Robotics Society of Japan as well as this project, who has actually led to the formation of this society. So this is one of the tele operations in an immersive environment. So please watch the video. So we are using a haptics device, as you can see it, to manipulate a robot which is a little farther distance here on the top right. And actually, we are trying to control the virtual robot, which is at the center of the screen, and then to take care of the delays. These kind of things have been attempted, that whatever control is done to do the virtual robot, the same signal goes into the real robot which is behind. So now we are trying to adopt the technology, even though it was for nuclear at that point of time. Now we have a very strong medical activities beginning here. I will share a few concepts or the slides later on. Then in the manufacturing setup, assembly setup, we have this force following robot. We know the robots are typically used in cages, so we wanted to make the robots as a human friendly. So we are trying to take care of the current passing through the motors to have this kind of flexibility implemented. And this is 2 industrial robot put it in a master slave manipulation mode. And finally, understanding various aspects of the compliance in the robot. So we attempted the peg-in-hole operation. by introducing four-stroke sensors here, so that we can trace this circular hole and then determine from the force plots that what is the center of the hole based on the resistance coming and then insert the component. Now the C part. Last year, or in the 2019, there was a call for a proposal by our government of India to start the technology innovation hubs at 25 institutes in India, and they have to form a Section 8 company, which means a non-profit company. So we have been assigned to work on the area of collaborative robotics based on our experiences and the proposal submitted. So this is our website. It talks about various activities, the research we are trying to conduct, the kind of online courses we want to do, the kind of international collaboration. I am happy to some of Professor Shibata and other professors have shown agreement to work with us, even though we have not really started anything concrete. Maybe we should do it. 170 crores rupees means about 20 million US dollars for over 5 years, and we have about 100 people coming and interacting with us. And these funds are available for international collaboration as well, except that hard cash cannot be sent to the foreign land, but the foreign professor can hire an Indian student or Indian researcher in India for whom the payment can be made from our company. So what we are working presently is, as far the research is concerned, other than the skill development activity, so we have classified 50 plus interest from the professors into several categories: Industry 4.0, intelligent and secure communication, drone applications, rehabilitation robotics, healthcare robotics, medical simulators, human-robot interaction. So two of the panelists here are actually helping us. Because Ashish Datta will be helping in the rehabilitation robotics to lead the team of 8-9 projects around the country, and Ashokar will be helping us in the medical simulator as the leader of these things. And we have human-robot interaction. We have one professor from Japan, from Shibaura Institute of Technology, Professor Matsuhira, has shown keen interest to work in this team in order to provide the tele robotic technologies which they are working on. As I said, no money will be transferred to him, but if he comes to India, we take care of. If his students want to come, we take care. Similarly, when the people go there, that is the way collaboration happens. What has impressed me in the lecture by Professor Harada is we are thinking of medical cobotics center in our off-campus, which is about 50 kilometers from here, to impart training and R&D related to the medical surgical robots. And this would be one of its kinds in the country, and we would like to take a lead through this company by investing maybe the simulators or possibly the buying one robot if possible, whether Da Vinci or CMR or some names also mentioned by Professor. So we would be very keen to see collaboration with University of Tokyo in terms of medical robotics. One just demonstration I wanted to show, which we have begun as a part of this activity, is tele ultrasound to be carried out. So this is the same haptics device as you've seen at the beginning. So we have a cobot from Universal Robot, as you can see here, and here a volunteer. So the USG, the ultrasound probe, is a 3D printed because some testing of the algorithms are going on. And this is in the factory setup. Later on, it was taken to the hospital, and about 20 plus volunteers have been tested, and they have given their feedback. And we are now in the next phase of improving it, in terms of the design, the orientation, and the doctor's comfort, and so on and so forth. And this will help us in not only for the COVID situation, but post-COVID also, take this kind of healthcare diagnostics to the remote places in the country as well. This is just to mention that in India, particularly at IIT Delhi and other institute, we have to put a lot of emphasis in terms of education, because we have a large young population. So this is my contribution towards that. This book, this is the second edition, the white color, and the green is the first edition, in order to assist helping the students to grasp the subjects well, like the kinematics and dynamics. We have a software called Robo Analyzer, and Rajiv, who is helping in this workshop, has been my master students, now a faculty. He is a key driver taking care of this software. Just to show you a glimpse of how this software works. This is a priceless software, can be downloaded free of cost. And starting from understanding what are the DH parameters are, right, and the forward kinematics and the direct kinematic, inverse kinematics. For example, this is just a two-link arm. Now, if you wanted to understand what is the forward kinematics, so this is the way it looks. Then we have a virtual robot toolbox, which has about more than 15 plus industrial robots, taking all the standard KUKA and Kawasaki and all such things. Then we have an inverse kinematics module, so here is the virtual robot module, for example, ABB, IRB. It gives you some basic information, and then you can run in, joint control mode, or you can give a Cartesian control, so you can say start, and you can see how it is moving. And this is the end effector configuration, the position, the orientation, and the homogeneous transformation. So this is a more than 10 years old kind of software. We are improving every month, you can say. This I already showed you. I skipped this page. So that was about our laboratory activities, and then our educational part. But then education, in Japan, I know Professor Matsuhira sends every year some students on the project-based learning. So you have a lot of emphasis. In a similar line, what I call is the competition-based learning, not the project-based, because project-based, the zeal of the students to win something is somewhat lacking. But if it's a competition, they know they have to win. So Robocon, again, Japan originated contest by NHK, started in 2002, the international competition. I've been strong supporter of this thing. 2019, we hosted at IIT Delhi, and 2022, we'll be hosting in India, the ABU competition. And just a glimpse from here. So 2019 competition was held in Mongolia. So generally the theme of the game is taken from the country which hosts it, like 2022 will be from India. Okay. And you can see the kind of challenges thrown to the college students, they are enormous. Like as you can see, this is a working robot the students have to build. So to me, this includes all aspects of engineering which are typically learned in an undergraduate course, and that would give a lot of motivation to the students, to learn what next. So that's the way we try to preach this thing very strongly. And in order to reach to the masses, we wrote a small fiction book called Rugby, Robotics Competition Knowledge-Based Education and Engineering. No equation here, just a story form. So you can see how the robots are moving. So all aspects of engineering, from concept to design to manufacturing to debugging, and at the end, the strategy, the robot which you see in front of you, has been the very popular team, but the other team, which was not so popular in the final, it won because of its strategy. In order to emphasize this aspect, the reliability and robustness to the young kids or the young students, so we said, okay, after Robocon competition, what next? So 2009, we started this journey by saying that, okay, if I keep the robot for 24 hours unattended, what happens? So as you can see, in those days we were following lines, so line following robot. So we tested the electric circuit reliability, the robustness. That okay, after 7 days it was getting burnt out and stuff like that. And this is 2019. We made it autonomous, as you can see in the right hand side. And for your information, as you can see here, IDEX 2019 in collaboration with Matsuhira, this robot was has a communication from the exhibition site in Tokyo to be able to control. They could not control the robot, but certainly they could successful, quite nice collaboration. However, journey continued, and then 2019, the same year, Romulus 5, that another version of this robot has been adopted by a company in India called Peer Robotics, and he claims that this is the true collaborative robot, as you can see in this video. And so the base, you can see it's the same RoboMuse 5, and then you will see towards the end. Oh, okay. It's, I just wanted to go fast forward. Let's see if I can go fast forward. Yeah. So here you will see someone is coming and trying to push, but then he will not put all his forces here. Okay, let him. So you can put it in autonomous mode. You can put it in a collaborative mode. So this is still in autonomous mode. Now I think it is switching to collaborative mode. So the guy picks up the boxes, and here collaboration comes. He's not exerting his whole effort. It's just showing the intention, and the robot is timing. It's like a power steering system. So we have several other companies. There is one drone company in the campus. In fact, tomorrow they are going to demonstrate with the 50 drones a formation of ships. So it is a challenge they have taken for the entertainment and farming aspect. This is our IIT Delhi campus. For those who could not visit yet, have a very brief glimpse. So this is an advertisement. We're doing it for our Diamond Jubilee celebration last year, and this was Independence Day, the 15th August. You can see the flag hoisting activity happening there. Yeah. There is one more company, Vectros. So we interact with these startup companies to this, and in order to emphasize the skill development. So in India, we have the largest young population in the world. So we do take care of a lot of skills. So on my personal note, along with some collaborators, we have started a competition with the Tejpur University, which we call self-driven, self-learning, and self-evaluating. So there will be a paper in this conference, and this is some slides from there. For those who are interested, can attend that session. So with this, I conclude. I talked about mechatronics. I talked about RoboAnalyzer software. I talked about Robocon as an experience of skill-oriented learning, which I also call it as an innovative teaching mechanism, and ROC, RoboAnalyzer-based competition, as a skill development activity. Acknowledgement to all our friends, students, spouses, and thank you very much for your kind attention. And I'm there in the session till 1 o'clock. So if there are questions, please feel free. Thank you very much.
Thank you, Professor Saha, for your wide-ranging talk covering research and student activities and the software developed at IIT Delhi. So our next speaker is Professor Ashokan T from IIT Madras.
There is some issue
You're
using
not able to
Chrome.
see?
If you are using Firefox, Mozilla, maybe can you
Yeah.
please share complete screen?
I have shared complete screen actually.
Yeah, but when
You-
we lost
you-
your audio when you shared. Can
Let
you
me
please
try
try it
again.
again? Yeah. I think we are not hearing you.
Okay, but we can't hear you.
We can't hear you. Sir, we had this issue earlier. Can you please try from Chrome, Google
okay.
Chrome?
So I need to choose that link, right? Okay. The
No,
link which is
you will have to exit from here and then again join using Chrome.
yeah, but I tested this. It was working. I mean, before we started the program. Anyway, so you want me to go back, go to
Or you can try a particular window and see whether it works. Share only one window.
okay. Then
In
let
the
me
pop-up,
close.
there will be full desktop window tab. So maybe you can try
Yeah.
only window.
I'm not able to see those files here in the select window option.
No, you open that PowerPoint. It will be shown.
I have opened it, but it's not coming. I have get only the entire screen option.
Oh, that's
Do it last time it came, no, correctly.
no. This
Yeah,
is,
when I opened it came actually. So my screen is. Can you hear me now?
Yes.
Okay, so I hope things works now. Is it
Yeah.
okay now?
Yeah. Okay. Okay.
Oh, good. Yeah, good morning, everyone. Good morning and good afternoon to all our friends in Japan. First of all, thanks to the organizing committee or AIR for this workshop and giving me an opportunity to speak about the robotics research at IIT Madras. And for our friends in Japan, IIT Madras is actually situated in the southern part of India, Chennai. So we are adjudged as the best engineering institute in India as per our Indian ranking for the last 4 consecutive years. So I'll be presenting a brief about the research in robotics, primarily happening in the institutes. So I'll be talking about the underwater robotics research, where we do the design, dynamics, and control of autonomous underwater vehicles. That includes the underwater robots, glider, etc. I'll be briefly talking about the work in aerial robotics, where we work on the design of aerial robots as well as on the path planning and control of aerial robots. Then briefly talk about medical robotics, where we are looking at the design of surgical robots, especially the teleoperated surgical robots. And as part of this, we are actually working on this hand tremor compensation and strategies for identifying fatigue-induced tremor, etc. And then I'll be talking about some special design of robotic systems, which is primarily a mobile manipulation, which is different from the conventional mobile manipulators. I'll talk about how the design of mobile manipulators can be made simple, but at a bit robust and less complex. And apart from that, we have faculty working in the area of RL and ML applications in robotics, though I don't have any slides on that, but we have a few faculty who works on the learning aspects and how these learnings can be used in robotics. So let me talk about this underwater robotics research. So I was involved in the design development and control of a 6 degree of freedom autonomous underwater vehicle. So as part of the research, we looked at the modeling and the simulation of underwater robots, 6 degree of freedom robots. So this robot is quite big. It's actually a commercial application purpose. Though it's not commercially available, but we were developing it for a 300-meter depth with around 15-meter length for the robots. And after understanding the dynamics, we designed the control strategies for the robot. So we came up with the different control strategies based on the requirement of the particular vehicle. And we developed these strategies for path planning. So we came up with a new method called improved line of sight method for path planning, where the normal line of sight method cannot be applied in underwater robotics because the robot has to just go on just above the sensor to collect the information. So any approximation or any path away from the sensor will be not useful. And therefore, we came up with this method called improved line of sight methods. And apart from that, we came up with a methodology for the obstacle avoidance also. So this obstacle avoidance strategy is different from the conventional method. So we actually came up with a multi-point potential field method in order to increase the safety of the robot itself, because the robot should be protected from hitting any objects in the water, floating or stationary or moving object. So we came up with an improved method called multi-point potential field method. So this was, and this has been published. And what you are seeing on the video is the first sea trial of this robotic vehicle. You can see that it is being deployed from the ship. And once it is deployed, it is fully autonomous operation. So once it is commanded to move underwater, then of course it will go as per the designed paths, avoiding the obstacles and following our improved line of sight method. And after that, we can collect it from the targets. This was the first trial, so very limited capabilities were tested, and this work is still going on. So we are trying to improve the navigation and control aspect of these robots. As part of the underwater robotics research, we came up with a new method for buoyancy variation. So most of the underwater systems use the weight change as a buoyancy method. So they pump water inside or they pump water from the vehicle to change the buoyancy, which actually is a bit problematic because of the seawater corrosion and all other issues. So we came up with a method of volume control, where the volume of the whole vehicle will be changed so that there will be a change in buoyancy. So as you can see here in this figure, so what we are using is the bellows. So the whole body of the robot is made up of metallic bellows, and there are electric motors inside, and these motors will actually try to compress or expand the bellows. So you'll get a change in volume, and whenever the volume changes, there will be an increase in buoyancy, so it will start going down, and then when you try to change the volume again, this will come up. So this way, you'll be getting a sinusoidal motion for the glider, and the power required is very less in this case. You don't need to have a thruster to do this. And what you are seeing here is actually, okay, there is a video. So this is the fabricated prototype, and then finally we tested this in the swimming pool to show that it actually works. The buoyancy variation is working. So now we are actually converting this into a commercial product. So we already set up a company to commercially develop this product and then use it for commercial application. Just got high endurance because of the power requirement is very less, and it is very silent. There is no thruster, so there is no disturbance to the surrounding medium. So we hope that this can be commercialized in a short span of time. And the second is on the medical rehabilitation robotics. So Professor Kanako explained about the surgical robot and the importance of surgical robotics in the current era. So we actually designed a surgical robot with two master arms of 7 degrees of freedom and two slave arms of 7 degrees of freedom, with capabilities for haptic feedback and a 2D vision system also. So we have a camera arm which carries the camera inside the body, and then these two slave arms, as you can see, these are the two slave arms which will be carrying the surgical tool, and then we'll be able to control this using a master robot, as you can see here. I'll get the details later. So this is the system diagram. You have the surgeon console where the surgeon will be sitting and then watching the video image, and then he'll be controlling the two master arms, and that master arm motions will be captured and it will be processed in the controller, and it will be passed to the slave robot. The slave robot will be manipulating the surgical tool. So this is the surgical tool we actually designed. This is our own design, a patented design. So as you can see here, we have 4 motors to control the tool tip, 4 degrees of freedom at the tool tip, and this part will go into the human body, and then the tool tip can be manipulated using the master arm. And this is the final design for the surgical toolbox. And this is the master robot. That will be having 3 degrees of freedom for positioning and 3 degrees of freedom for orienting the tool. So the surgeon will be holding on to this gripper. And again, we have a patented gripper design, which will be used for controlling the tool at the surgical site. So we have 2 such master arms. And then, of course, these motors will provide us, help us to provide the haptic feedback also. I'll just show you the video. The video of the whole system. So this is the master robot, which will be, so you can see the person is holding onto the grasper, and it has got all the 6 degrees of freedom, plus the grasping degree of freedom. And all these motions will be captured using the encoders, and then you can find out the actual Cartesian motion of the tool tip, the grasper, and that will be passed to the slave manipulator. So you have 2 slave arms. So this is the laboratory prototype, so it may not look very nice here, but of course, if you change, when we convert this into a commercial product, we can actually make it much more attractive. So this is the slave arm with a remote center of motion mechanism for getting the trocar point as the point of insertion. And then we have this tool, the surgical tool, as I mentioned. The surgical tool will go into the human body with all the 7 degrees of freedom possible at the tool tip. And this is the master slave manipulation. So you have the master robot is being controlled, and the video image will be appearing on the screen, and then you can actually see that the slave robot will be manipulated, or the tool can be manipulated as per the requirement by the operator. So this is a complete master slave tele manipulation. So the tooltip transmission is through cable. So you can see that the motors are all at the distal ends, and only this part will be inside the body, and you can have very fine manipulation of the tool at the surgical sites. So we are now converting this into a commercial product. So through that, with the help of the Technology Innovation Hub or the Cobotics Center at IIT Delhi, we are planning to have a commercial product designed and developed in the future. Just to show you that we have actually work on do some active hand rehabilitation work also. So this is a simple device with a control with a single motor for controlling the fingers. So those who are having difficulty in moving their fingers because of some neurological disorder, so this device can be used for controlling the fingers. So now, depending on whether we want to have it as a remotely operated, or it has to be a program, so both are possible, or we can want to use the other hand as a control device. So there are multiple possibilities, and again we can actually develop this in a commercial way at a later stage. Okay, and the other important work what we have taken up in the recent past is the design of multimodal robots for field and industrial applications. So multimodal robots are the robots capable of doing multiple modes of locomotion, grasping, and manipulation. As you know, any manipulator with any industrial mobile manipulator requires to have the capability of mobility, manipulation, and grasping. So these three things need to be there for any mobile manipulation. And most of the existing or industrial commercially available mobile manipulators will actually a combination of these three. So you'll be having a manipulator, you'll be having a mobile platform, and then you'll be having a grasper attached to it.
Did we lose? We have lost him, it looks like.
Shokan, can you hear us?
Can you hear me? Hello?
Yes.
Hello?
Yes, we can hear you.
Hello?
Yeah, we can hear you.
Hi, Ashish?
Yeah, we can hear you. Can't you hear us? Are you muted or no? You're okay.
Can you hear me?
Yeah, we can
Yes.
hear you.
So you can continue, sir.
Yeah, you can continue.
Can you hear me?
Yes, we can hear you.
Hello? Ashish, can you hear me?
Yeah, I can hear you. So please continue.
Oh, sorry. Yeah. Okay. There was some problem, I think.
Yeah.
Okay, so I hope I was explaining about these multimodal robots, and we are actually trying to design a novel multimodal robotic platform which incorporates grasping, manipulation, and locomotion. I'm getting some echo.
Yeah, you can continue. We can hear you.
Okay, fine, yeah. Okay, so the design concept for the multimodal manipulation is that we will be using the conventional, the concept of conventional manipulation. Then we'll be using the grasping mechanism. But what we are trying to do is to combine this into a single unit and then get the manipulation capability. So as you can see here, the main design concept is basically these two graspers. So you can see there are two graspers which are
Screen mode, presentation mode.
Yeah, I'm in
Okay.
presentation modes. Can you see?
Okay,
Yeah, you
we
can
see.
continue, please.
Yeah, no problem. Yeah.
Yeah. Okay. So the main design concept is here. There's two graspers. The graspers can act as a grasper, a manipulation device, as well as a locomotion mechanism. So we have two such graspers, and these graspers are connected through serial linkages. Now we'll be using this as a mobile robots capable of manipulation, grasping, and locomotion. So how we get this? So we can actually use these two graspers. So when it is in this mode, it can actually stand on one leg and then do the manipulation, or it can actually stand on both the legs and then have a rolling motion or a walking motion. And we are using the same motors for all these activities. So this is the grasper design. So as you can see here, this grasper is especially designed with the two jaws, and each has got the 4 sheaves, and there is a belt drive. And by properly controlling these sheaves and the belt, you will be able to have the grasping. You can have a in-hand manipulation, or you can just have a grasping, or it can be used as a wheel for locomotion, or can be used as a leg for walking. So these are the capabilities that we have in this design. So I don't go into the details of this design. Let me show you the capability. So this is where actually we can use it for the object manipulation, or the object can be fixed and it can be used as a simple grasper also. So both the in-hand manipulation and within-hand manipulation can be done using the grasper. And how is it done? So as you can see here, this is the first prototype of this robot. So you can see here, this is the these are the two graspers, and they are connected through the linkages.
Ashokan, your slide is not changing.
Oops. It's not changing now?
Not in full screen. Yeah, now we see slide number 19.
Yeah, that is the one I am using. Okay. Yeah. So can you see the video?
No, sir. We are still looking at the PowerPoint, which has left side preview and then the slide. Maybe within this you can play. Come out of slideshow.
Yeah.
Yeah, here only if you can play.
Yeah.
Is it visible?
Yes.
Yeah. So this we can see that now it's actually in a wheeled locomotion mode. And this mode can be changed to a grasping and locomotion. So you can actually hold an object and then do the locomotion. So you can do the object manipulation, grasping, and locomotion. So that is the first mode of operation. And then we modified this to get the next one is the brachiation motion. Or brachiation is that hold one object and using one grasper you can hold, and the other grasper can actually actuated to hold on to the next object. So we'll be able to get a brachiation motion using this mechanism. So grasping and brachiation can be achieved using this method. And the last one, what we can do is with this is the walking motion. So you can actually make this as a walking mode. So in walking mode, what we do is that we'll allow the robot to stand on one leg and then change its center of motion. And by controlling the motion of the center of motion, another leg, this leg can actually be moved to the next position, and then we can have a walking motion for this. So both all the locomotion modes of rolling or wheeled locomotion or walking or brachiation can be achieved along with the grasping capabilities also. So the grasping, manipulation, and locomotion capabilities made into a single system. So this is finally further being developed to get a full walking motion. We are still in the process of developing it, and we see that this can actually, once we develop this in a full product, there will be a lot of utility for it in the industrial applications. So moving on to the next product or the next topic, which is the aerial robotics. So most of the people do the quadrotor design, but what we have done here is to have a different design for the quadrotor to have increased endurance or to reduce the size of the robots with the same kind of capabilities as in other cases. So this one we called as vertically offset overlapping propulsion system, where the rotor wings are actually overlapping one over the other, so that we can have an increased diameter for the propeller and get more power for the travel. So that is how we actually designed this quadrotor and improve the endurance. So this is the prototype of the overlapped propulsion system. So there is an overlap, and therefore there is an offset also between the propellers. And so we try to understand what will be the effect of such overlap and offset. And we found that there is not much of power loss. And then we showed that this can actually do can actually increase the endurance of the quadrotors by having an overlap propulsion system. So we did the trials using, within the lab for testing the losses, and then finally did a test in the ground. I'm not sure the video is working. Yeah. So we did this test to show the capability of the quadrotor for I think video is not working well. So, but we finally proved that this can actually have an increased endurance. Yeah, as you can see here, it's carrying a payload and then showing that the payload can actually be increased by having this mechanism. Okay, so before concluding, let me present some other related work in the area of quadrotors. So in the guidance, navigation, and control, this is from the lab of Professor Satatal Ghosh in the aerospace department. So he's working on the planning and motion control of aerial robots. So this particular work shows the obstacle avoidance and dynamic collision avoidance of multiple quadrotors. When multiple quadrotors are deployed, how can they avoid the dynamic collision? So this particular work is related to offline motion planning and online reactive motion planning to avoid obstacles. And this is again additional work on path planning. So it's actually shows the target localization in 2D and 3D environments, as well as landing on a fixed or a mobile platform. So if a rotor aircraft has to land on a moving platform or a mobile platform, what kind of control strategies can be employed? What are the strategies need to be developed? So this is this work primarily looks at the landing issues. So these are the works from Professor Satatal Ghosh. So I'll conclude with this presentation with this slide. So thank you very much for your time, and sorry for the difficulties encountered during the presentation. Thank you.
Thank you, Professor Ashokan. So our next speaker is Professor Ekta Singla from IIT Ropar.
Yeah, thank you. Am I audible, please?
Yeah, you're audible, yes.
Okay. And the slides,
Yes, they're okay.
it's in the presentation mode. Is it all
Yes.
right? Okay,
Yes.
thank you very much, Professor Ashish, and everybody. A very good morning to all the Indian participants, and a very good afternoon to all our Japanese friends. And it is certainly an opportunity, and I'm sure that it will be great to have this sharing with you, and the rest of the 3 days will be very effectively utilized. Okay, so IIT Ropar is relatively a new IIT in India, and as I say that it is around 13 years now. So we call it as the second generation IITs. So relatively, I mean related to the 3 other speakers which we have, like from Madras, Delhi, and Kanpur. So that is why I have just used 2 or 3 extra slides to advertise the institute, because I would like that people should be here. In totality, I'll be speaking about the umbrella Punch Robotics. That is because it was a recently established institute. So when we were having only 7 to 8 faculty members in the Department of Mechanical Engineering, I never found anybody really who would be working exactly in robotics. So in 2016, with the help of our RSI members themselves, we have established Punch Robotics here, which is a platform, and I'll be speaking about it, and in particularly the research areas related to the modular concepts, which we are focusing. Of course, there are many other directions in which students and the faculty members are working. I'll be just touching upon a few. And yes, as I just mentioned, we are at the northwestern part of India. And if I just would like to give a glimpse of our new campus, which we had shifted just 3 years back, because before that we were in a transit campus. So although it was established in 2008, but 2010, it's like now only just 3 years back itself, we have shifted to this campus. And yes, I'm using a few more pictures because it will be nice that whenever next in person we'll have any conference, and then our participants, they must think about visiting the campus. And yeah, this is the Satish Dhawan block, the Department of Mechanical Engineering, where I belong to, and my lab. Just a glimpse, because of course every year people come and go, and in particularly I am working both in industrial robotics as well as touching upon many of the other areas in which where modularity can be incorporated. But before that, yes, again, because about the location, as I said, I'll advertise a little more about the institute, because for our international participants, particularly the speakers, another reason that why you must visit Roper, which is less likely to be popular, is actually because this is one of the biggest sites belonging to the Indus Valley civilization, and we have a museum here. I'm sure you would like to just add in your next visit plans. And yes, there are many of the tourism locations around, and including the Golden Temple at Amritsar. And more than that, we were very fortunate enough that we have 10 in a very nearby, like around in the area of 30 to 40 kilometers itself. We have 10 more national labs and institutes, and which is helping us to develop the collaborations and interdisciplinary working both in medical as well as in materials, etc., in a very good pace. That is why we have got very good rankings also, both nationally and internationally. Uh, Now, about punch robotics, because as I said that in 2016, when we found that people are working in distinct areas, it was important to club them that they had some idea about robotics, but they didn't know exactly where to start with. That was the time when we actually started with the PR community, which is now increasing, in which we do have all industry faculty members and the students from different programs, and it is helping to uplift the sector of robotics, as well as because mainly people are working, all the faculty members may be into additive manufacturing, they were also into materials, the experts from different directions, they are now contributing under this umbrella of punch robotics, right? So what I'll be doing is, like, of course we had access of this PR studios not only to the IIT Roper students, but to also around. There are so many institutes and colleges where maybe sometimes very few people are working in robotics, but now we are trying to club them. So this is one platform which is helping. And just to give a glimpse of some of the directions in which some small and big projects are working before moving to the modular concept. And this is actually like, okay, students have also utilized the facilities to work with the this humanoid, may it be into the speech gesture mapping, as it is just mentioned, because I'm just giving the glimpse, and also for its movements, its arm movements, manipulation, etc. So there are 3 or 4 projects which are related to the humanoid. And similarly, in the vision sector, camera pose estimation, this is just the recent. I'm just showing the ones which are published and not just taken up by students, so that because it is still just 3 to 4 years old. But yes, I just picked up some. For example, the second one, this is in which we had seen that in many of our works we needed the entire the simulation or some collision avoidance, etc. in the environment. Many of my own works were related to the realistic environments. So how to get the environment built, like at least the STL files quickly using the scanner itself, without using the professional scanners. Now we have used the cameras itself, so that by taking some of the pictures, how we can construct the 3D scenes directly and use them in our other projects. And majorly we are working in the design analysis part, mainly may it be using the serial or parallel linkages. And modularity and reconfigurability manipulators, I'll be speaking more about it, how we have utilized it in 1 or 2 versions of modular libraries I'll be showing. And yeah, recently, because in the area we have got 1 or 2 like international, as well as some projects from defense and the rehabilitation center from Delhi, where we are working towards towards how to just use the task base, because mainly you'll find that our work is related to the customized robotics, in which how to for any type of mechanisms can we actually incorporate that, how we can have more mimic, just following the actual human motion. And this is just, again, I would say, some of the projects which are recently taken up in 1 or 2 years. And mainly I would like to just go further. Yeah, as I mentioned, in the right side, you will find that in the other works which are taken up mainly at the research directions, there we normally take up two cater the customization. And for customization, the majorly we take the task-oriented planning, the task planning, optimal synthesis, and also collision avoidance, minimum interference, unconventional parameters. We are also taking care of the parameters which are unconventional in nature. I'll be just showing about how we have used not just 0 and 90 of alpha of BH parameters, but we are trying to give unconventional architectures for some of the intricate this environment. And reconfigurability is what we have, what in my group we have actually utilized or you can say explored in the last 3 to 4 years. And first, Moir is my own library, because I just mentioned modular and intelligent robotics. Mark 1 is actually the modular library which I would like to propose. This is how I started in 2010 in this institute, where in the first 3 to 4 years we were more into task-based planning, because we had looked for all the cluttered environments and how we can actually go for redundant and modular robots. Mainly we started with the redundant arms. You will see that how we have, for a cluttered environment, of some of the realistic examples we have taken from, say, from some power sector, power plants, or some of the our own labs. We were taking some of the cluttered environments and trying to see if we can actually develop a basic or synthesizer robotic system which is redundant in nature. But it was all getting that only into the design side. We have seen that the unconventional designs, it was easy to just show in the simulation, but not really applicable when we actually see that we need to develop a robot, because the parameters were not exactly 0 and 90 or perpendicular to each other. So there we started with our work in around 2013 for modular library, and this was the first, I would say, set in which we had seen that all the systems, that how exactly it will, that given a particular task, how exactly we will be utilizing. First, we should know that, for example, here if at the right side, rather I'll use this case study because it's from that first student of mine, 2013 to 15, 16. So basically there we had seen that if there will be a cluttered environment and we look for some robotic assistance for that and develop a system, of course not, of course using the modular robots, then what we do is that we first take the some as an assumed model of that, for example, left side. Now for that only I mentioned that rather than now making a solid model separately, we were working on how to scan and directly using the pictures and how to construct the 3D construction. What work I showed earlier will be utilized here in this works also. And we had given that how we will be choosing, because using the modules which we had developed, with these modules had been developed, which I showed in the previous slides, the first set of modules. They were, in 3 sets, like the 3 types of motors, accordingly the 3 lengths, and Y3 that everything was published related to that. What are the extent of robotic arms which we would like to develop? For example, till 7 to 8 degrees of freedom. Then what is the extent of payload, and can they carry each other? Why we cannot have same type of modules, and why do we have distinct, and how many, and for each module we also compute that how many more number of such modules optimally it can actually check. So everything was used, so enough of optimization techniques, different both classical and evolutionary for such methods. And by normalizing minimizing the talks, we had seen that how exactly for given task, if we just use the modules, then what will be the right modular manipulator which will be helpful to use in that particular cluttered environment. So this framework was ready, and recently in the same direction, we had actually developed the Mark II, we will say that improved library, because the first version was certainly heavier, and we had of course noticed many of the issues related, particularly it was not minimized, we had not checked the dynamics of it. So recently now we had worked for, analyzed, I'm not showing the details here, but yes, we that how the next, we have seen how the architecture of the entire each module needs to be optimized, and we have seen from the dynamics perspective also, because earlier we were looking at mainly only the static or the kinematics. So here it has to be seen that again the entire strategy I'm just skipping this, but showing you this particular library, because now the set is ready. We have tried to make it, of course, lighter, and the actuators are changed. Earlier, we were using the heavier version, which were not required, and now, because in modular library, it is very important to select the actuators first, and because they need to be appropriate, or you can say optimal enough to do the job as well as to carry each other, because the weight of the actuators or the gear system, etc., is also playing role. So Anubhav here is my recent student who has actually developed this unconventional list. And here I would like to mention that we are not developing the robotic systems like how they are unconventional, because as you just see here, they, when they are connected, we can actually change the alpha to some different values rather than 0 and 90. So uh, of course we can actually develop, we need to just compromise something like the rigidity, but basically to work in the cluttered environments and to help in the service robotics and for maintenance, where we are trying to take one or two case studies also recently. There we are showing that how the same modules can actually be able to, they can be assembled and reassembled or reconfigured to get different types of configurations which are required. So we have actually tested for many of these standard configurations which are required, and also we have incorporated particularly for unified modeling, because at present we have made it a point that earlier it was not so, that we were not using the similar robot operating system like ROS. But now from the last 2 years, we've also made it a point that why not to make it more standard. And what is happening is that using the URDF files and the standard, these platforms, we have now developed these arms, modular system, where anybody can actually utilize it for, say, given DH parameters and modular systems. If we know that what exactly is to be required to be assembled, then which modules will be able to, so all that, like, there are limits which are already planned. So everything is done, and after that, for a particular task which could be complicated, and for a particular for an environment, it actually develops one system. And in fact, not only this develop, if you want to assemble on your own and then get your modeling, both kinematics and dynamic modeling, which for the system you have developed, that unified modeling is also done through this standard, in this standard operating system, that is ROS, so that it can be now utilized by as open sources or by other people who are working in the same area. So just to show you this glimpse, because in one of the case studies, yeah, we have tested for a few case studies where we see that how the same modular system can be utilized. And here you will see that given any particular say the right side, any particular cluttered environment, if we use our earlier design systems, because I had been working, which are not shown here, for the synthesis, for the optimal synthesis. So we, for a particular cluttered system, which optimal DH parameters or which optimal robotic arm will be useful for the given number of tasks. So tasks we always give as some standard points, as I have shown in the very beginning. And for those, if we just see that, okay, this is the system which may have 5 degrees of freedom or 6, and which modules is also being computed, because that also take care of the optimal, all the optimality in talks, right? So there, then we can actually develop, and first we can simulate both in the simulators which we have prepared, and also using the actual robotic, because this modular modules which we have developed in our lab, that we can actually demonstrate. So one of the demonstrations, for example, here, this was a cluttered environment, and how it will be the path planning, etc. Also we show through the ROS and the peripheral other platforms. So here, if my video is okay, one second, it will take a minute, like how exactly the modules work. Is the video working, please?
Yeah, the video is okay.
because the entire idea is that using the other work, that if we get any realistic problem, environment in which, so we can actually scan it, get the environment, get the robot design ready through our design algorithms, and then once it is, we know that what is the which DH parameters or which modules are to be used or assembled, then how straightforward at least to do the demonstration in our present version. So this is our second version, which we are trying to show that at different configurations. So I'm just fast forward. Okay, it is anyway going. These are all 3D printed in the institute itself. So certainly now we are collaborating with one or two industries to look after what are the shortcomings and what next we would like to work with our Mark III. And one or two industries have shown their good interest, and now it will be good for us to move further. And after some of the many of the feedbacks which we have collected on it, because we would like to increase on its strength also for the payload capacity, etc. And you'll see that similarly, the person will actually show in the, this is one configuration, and now the configuration will be changed. So here the alpha is now neither 0 or 90. Now the alphas are working at different values, so that we can actually work in as required for the unconventional systems for the cluttered environments. So from here, I would like to also mention that the same concepts of, because in totality our groups are working in modular synthesis itself, not only because earlier the works which I have shown was mainly in the area of procedural arms, which we are also connecting to the industry for, where we know that because of the change in environment or any new system, suddenly you would like to change in the robotic configuration. So there we have connected. Similarly, now not only the serial, another student of mine, she's a part of Punch Robotics. So Sakshi, we are working with the modular synthesis with not only serial, but we have the loops also. We also see that how we can use the modular primitives having four bar loop or 5-bar loop, and then connect it together with serial. So we have actually developed a system, a modular system, in which we can see that serial and the parallel loops, they can be connected together. We are still at the planar robotic system, planar mechanisms only, but yes, particularly we are working for, because I got 2 projects but in the rehabilitation devices. There we see that how for a given exercise base, because as I said that we are working on the rehabilitation exercises, already 1 or 2 speakers have already spoken about it, which were very interesting, because we are in association with the rehabilitation center at Delhi, and there we have seen that how manually people are helping for the rehabilitation exercises, which is quite cumbersome. So through this slide itself, I'm just showing the entire process which we are working upon, because taking the trajectory of the 2 or 3 exercises one at a time, presently at the sagittal plane only at present, what we are doing is that can we develop such a system which is again customized for doing an exercise or for helping in an exercise for a particular person, will be just planning the doing the synthesis, which is the first step, which is and then for given primitives, and then this particular robotic arm is developed, for example, only in the sagittal plane. At the back, we are also working on the coupled on the that how to improve on the misalignment. So I'm just mentioning some of the recent works which we are trying to do, that how we are improving on the architecture and particularly the motion, using some passive joints also at the back. And yeah, when we are using all these hybrid systems, there we also see that we explore with many of the systems which sometimes we don't come into our mind. So what we do is we also have another work where you starting from the just generating the different architectures using the primitives, and then we see that how the same automatically in using our algorithms, we will see that okay, which are the active and which are the passive joints, and from there the automation in kinematics and dynamic in this we have just developed for the kinematic model. and that too using the performance criteria will be computed automatically, so that we can actually compare among the different generated configurations. And that is also helping us now, because in this rehabilitation work we have used 3 or 4 configurations where we need not to like any designer need not to start from the scratch of the models, and these unified modeling techniques using the modular primitives, we are using it, that how quickly we can actually analyze the different mechanisms which are developed using the modules, and then we can actually see if they can reach the task plan, because these are the points. For example, just symbolically I have shown here that how that if it has to go on these points which we have gathered for the task planning for the more human motion which has been taken. So how good or which particular configuration is working better, right? Of course, at present we are working only for the kinematic analysis or kinematic performance, and even in that it is helping. And coupled, we also look for the coupled mechanism, because majorly in one of the project we are working with the defense also for the leg exoskeleton, which are not used here. But there it is important, because we all know the problem of misalignment, because whenever we are using any particular robotic system, and we are also trying to do with less number of degrees of freedom, but if we'll go with it, certainly it will have the problem of compatibility with the human arm, and we are just trying to show it through simulation that how exactly the coupled system can be analyzed. So we have used here the screw theories and try to give the entire the mechanisms which are unified models for the coupled analysis. So here I'm just clubbing that what is the entire process which this recent work from the last 2-3 years only, we have tried to give only the model and the simulation, where we take the data for a particular person, and then using that we just estimate the trends, and accordingly, and also which exercise. Also quantitative model is given by the student, that this model will help us to quantify how much is the torque required, because given a particular strength, because so that which exercise and for how long it is required can also be given a priori without the help of any expert. And this is also to assist the experts, because we are working, as I said already, with some experts in Delhi. So they said that it will be helpful, particularly for the training of the next experts. So given a particular trajectory of a human arm, then how exactly we can work on the different primitives can be used to actually develop a particular system which will be suitable for that human person. And we also do some workspace analysis, because it is not that only for that particular trajectory it will be helpful. We have to check the performance around in the entire workspace, and then develop the particular system. And so here also I would say that it is almost towards the customized robotics, so that can be club it. Next one or two, some of the works which I have not shown here are actually to make the prototyping directly from the primitives, so that if we know which is what system is suitable for a particular person, then can we customize it quickly or develop it quickly using the modules. So that is still in process. And similarly, we are working for the vertical farm setups, because we had seen that, because the library which I have shown, that actually this is just a recent work which we are trying with the Kinova cobot, but we would like to develop a library which I have already shown for taking care of the different agriculture processes which are required only for the vertical farms. The idea is that in the vertical farms, it's all actually, I'll better take it here. The farms are at present they are used only for 10 to 15 or 10 to 12 of height, and the robots which are in use are only which are working on the ground. So it is important, and also they are normally not the customized robots, but they are mainly the available arms which are utilized for this purpose, which is expensive if we would like to use everywhere. And looking at the Indian agriculture, where we are also we need to be having economical systems, there what we are showing is, this is just the concept, the modular concept, where we see that not only in the layout, but height also we would like to at least make double or triple, so that even in the less space we can actually use the robotic system which can work on the rails. And there for each module, what I have shown here is one module, the concept, and for each module or modular the library will be able to work, and then of course it will shift its base and actually work for the next. So all the processes which are required may be related to seeding or transportation, or we are working on what are the different grippers required. We are also working on different end effectors which are required for the purpose. For example, just one which is shown in the right side here. But yes, this is again in the initial stage, and just recently, a few months back only, we have made an experimental setup. So I've not included it here, but I'm just showing that how what we are trying to give customization or modularity even in this, because these all this here we are testing to begin with only with the Kinova robot which we have. But as I said, our vision is to look at the modular library which can take care of many agriculture processes, but only for the vertical farms, because the choice of the plants will be very specific, right? So it's not the field robotics, like not really the heavy duty. And here finally, I'll also would like to mention here the modular concept, which, because as I said, different people also were working in different directions. So we were clubbing together that how exactly their expertise can be useful. And here I've mentioned is the agriculture at the top, but actually it is actually into the surveillance, because we would like to give some robotic skin for establishing some camouflaging devices, and there just to follow how natural camouflage work, we are using the electrochromic devices. I present some of the research related. In here, a professor who is into materials, Dr. Prabhat, he is actually working with me. And in the other works, like Dr. Anupam Agrawal, who is helping, who is actually using his additive manufacturing skills, particularly what I work in earlier for the agriculture and for the modular robots. And we have Dr. Shrikant from aerodynamics. So different people who are working. I've not just included their pick here, but yes, this is all that how their expertise in materials we are trying to put up for the surveillance sector. And here you'll see that the polymers, we are just testing them, and the entire process is that how we can utilize, we can actually work on the different properties of those polymers, so that we can actually give. This is very recent, like kind of a few weeks back, we have shown that how we can develop or get the specific colors which are required, and how much time the color will stay, and if we want to change the color, how much time it will take. So all these testings are still in process, and what is the entire ways that can we actually develop skin which is modular, so that we can have this camouflaging skin which is made up of different ECD and just a 4x4 or a 5x5. We have at present seen that for these, the size of the convert minimum is 2.5 inch. So can we actually develop? We are working towards such kind of platform, but yeah, I've not given because they wanted to patent it, so we tried not to put up the actual conceptual pictures. And so this is all from my side. Yes, it was probably shorter, maybe enough to present the IIT Roper upcoming things. And as I said, this is I wanted to particularly emphasize on the very active environment here under Punch Robotics. And thank you very much.
Thank you, Ekta, for your nice talk. I think there is a question for you also, so please answer the question in the Q&A parts. Okay. Yeah, so thank you for your talk.
Yes, thank you very much.
So now we have the last talk, that is myself. Okay, so it's 12:15. We are running late by 15 minutes.
Okay. How to, we need to respond now, or I'll be answering later?
You can answer later, it's up to you. My screen. Is my screen visible?
Yes.
Yes.
Okay. So good afternoon to everybody, and I'm the last speaker. So I'm Ashish Datta, and I'm a professor in the Department of Mechanical Engineering, and I'm also the Dean of Infrastructure at IIT Kanpur. So today morning we have all met at IIT Kanpur virtually. So this map shows Japan on the extreme right, and IIT Kanpur is somewhere near New Delhi, somewhere in the middle on top. Okay, and so we have met virtually. Hopefully next time we'll all meet in person. Now, the broad areas of robotics research in IIT Kanpur, the way it is divided is we have the Center for Mechatronics, which is an interdisciplinary center between mechanical engineering, aerospace engineering, computer science and engineering, and electrical department. And apart from the Center for Mechatronics, we have the flight mechanics and helicopter laboratories. We have intelligent systems laboratory, where people look at things like AI and machine learning. Then we have computer vision-based laboratory in electrical engineering, and motion planning laboratory. So we have about 12 faculty members in the area of robotics, and it is interdisciplinary. So there are people in mechanical engineering, electrical engineering who are working together. Okay, so what I'll be showing you is interdisciplinary work may not belong to one particular faculty only. So the first is right from the basic dynamics of compliant systems. So most of the humanoid robots that are made, they're made up of rigid links. And we know nowadays that if we use series elastic actuators or we use compliance in any of the links, then what will happen is that the dynamics changes. Now, it has some advantages in terms of stability, in terms of impact. So here, basically, what we are looking at is compliant designs of biped robots, humanoid robots for walking, jumping, what effect compliance has on the dynamics and things like that. Okay, so design, control, dynamic simulation is all included. Now, in most of the research work, we also try and build systems so that at the end of it, we have experimental results, and then we can also try and entice the industry if they're interested. So this is an area of compliant dynamics of biped mechanisms. Now, most of the bipeds or humanoids that are there, they are very, very good as far as they work inside the labs. But the moment they come outside, then we have trouble. Okay. Now, so we're also looking at how to bring robots out into the environment, not only in structured environment, but also in unstructured environments. So, for example, in three-dimensional terrain, walking in places with ditches, crossing obstacles, etc. Okay, so this is extension of humanoid gait planning, motion planning in 3D. Now, we were also a part of the lunar rover mission. So ISRO is the Indian Space Research Organization. And in 2019, they had sent a rover to the moon. And we were involved in that in terms of the motion planning for the rover. So the rover is a basic rocker bogie type structured system, which has a manipulator on top. And our job was basically to do the motion planning algorithms for this rover. So we also built a rover, carried out various studies on dynamics, motion planning, control, and then some of these were actually tested on the actual rover. Now, so this is motion planning for the ISRO Chandrayaan-2 lunar rover. Now, there are some interesting problems here. The interesting problem is that the landing was expected to be on the dark side of the moon. Now, on the dark side of the moon, there is no light. Okay, so you need to see at night or when there is no light. So cameras won't do. So the other task that we were interested with is how can you make a map without using vision, computer vision. And what was done there is we tried to use structured light. So this is a lab model. This is not the rover that actually went, but this is a prototype. And what we basically tried to do is to use structured light, but you use a line laser. And then using a camera, can you scan the surface and then generate a map so that you can see in the dark. And once you can see in the dark, then can you do motion planning of this 14 degree of freedom system to go from one point to another point. Of course, you have to do dynamics control simulation. And so we use a 3D structured light approach for this, and we were able to generate maps, which you could actually see at night or when there is no light. Now, unfortunately, while landing on the moon, 2019, I think, or 2 years back, unfortunately, it crashed. And so we couldn't test our motion planning algorithms and also the visual generation algorithms. And next year, I think there is a joint mission between Indian Space Research and Japan Space Agency to go to the moon, where the lander will come from India and the rover will come from Japan. I think that is planned for this year end or next year. So this is about our studies on lunar rovers for motion planning, dynamics, control, vision-based navigation. Now, we also do work in the area of mainly for stroke rehabilitation. That is, you look at various motions, grasping, moving for the fingers, for the hands, for the legs, and then try and design mechanisms which can give you back that motion. Okay, so this is some research which we had done for design of hand exoskeletons. Professor Shibata was also included in this project. We started off many years ago, almost 10 years ago, I think. And then we have progressed quite a lot. Now, the objective is to study human motion and then build mechanisms which can give you back that kind of motion, essentially because we have a varying instantaneous center of rotation. And the objective of this study was that, or the hypothesis here, is that if you're doing passive physiotherapy, that means the person is doing exercise with a physiotherapist, but the person is not thinking, which means the brain is not engaged. So if you can force the person to think and bring it in sync with the physiotherapy or the physical practice, then our hypothesis says that the recovery is going to be much, much faster. Okay, and that is basically where we started off. So we have a hand exoskeleton, and we have a BCI, a brain-computer interface, which basically checks whether the person is thinking correctly. And if the person is thinking correctly, then only it actuates this device. Okay, so this is a part of our India-UK project in which we designed various kinds of hand exoskeletons for rehabilitation of stroke patients. And we also carried out a large number of clinical trials. Now, this is basically what the paradigm looks like. Okay, so we have a BCI cap, and on the screen, you can see a closed hand or an open hand or do nothing. And if the person thinks correctly, then only the exoskeleton actuates. Now, the hypothesis being then if it is in closed loop control, closed loop in the sense the person is also seeing, so there is visual feedback, the person is also feeling, there is physical feedback. So if this loop is closed, you are going to get a faster recovery. And we carried out clinical trials. Now, this has mechanical design, control systems, assist as required controllers, because if it is passive, the person will simply relax. He won't do anything. Okay, so you have to allow the person to try, and only if the person is not able, only then you should be able to help the exoskeleton. Okay, so that is where we try to design assist as required controllers, which are also for robots for assisting with humans. Now, we carried out clinical trials in India and the UK, and the results were surprising. So we know that for stroke, basically after 6 months or 1 year, you are not going to recover anymore. You do physiotherapy for 6 months or 1 year, and then you're saturated. Beyond that, nothing happens. Okay, but we took patients who are actually saturated after a year. So more than 1 year, 2 years, and we carried out this exoskeleton-based rehabilitation, and we found that 100% of them recovered, which is not possible as per physical physiotherapy-based physiotherapy. Okay, so these are some results of the experiments in India and the UK. And we have finished clinical trials. We are going in for large-scale trials now, where we want to try out in different countries to see the effectivity on stroke population. Now, in terms of the cognitive science, these results show that there is recovery, okay, but why is the recovery happening? Is it that the neurons are regenerating, or there is something else happening? So we also looked at the MEG imaging of the brain using MEG. And what we did find is something interesting, that not only is the neurons reorganizing at that particular location at the motor cortex, so we know where the motor cortex is and which actuates the arms or the legs, but there were new pathways which are being generated. And this is what we found, that the recovery is happening not only because of neural reorganization, but it is also happening because of these new pathways which are being generated from other parts of the brain to actually help. So we are looking at the engineering side, design, recovery, physiotherapy, but we're also looking at the cognitive sciences and trying to study that why is the brain behaving this way, or what is really happening at the brain level. Now, we also have done this experiments for the leg exoskeletons, and further trying to look at MEG-based studies for the leg exoskeleton also. We have extended our work on BCI-based exoskeleton, where we mounted the exoskeleton on a wheelchair, and we also have an eye tracker. Okay, so we have an eye tracker, which you can see here. So depending on where the person is looking, the wheelchair can be actuated, and the exoskeleton can also be actuated simply by using an eye tracker. Okay, so we have gone one step further in trying to provide locomotion ability to stroke patients. Another extension of this is something interesting, multimodal interfaces for communication and rehabilitation. Now, if a person cannot speak, okay, but you can enable a person to communicate by using this eye tracker-based communication interfaces. So this is basically for in the Hindi language, that is Indian language. So simply by looking at the screen, the person can actually type sentences for a person who cannot actually speak or cannot use his or her hands. Okay, so this is something which we had done using eye tracker for Indian languages. Now, this is the other area where a lot of people are working is AI, machine learning. So there is Dr. Behera, who works on machine learning applications to robotics. And they look at things like autonomous grasping, which is what was done for the Amazon picking challenge. Okay. So if there is a cluttered environment with a lot of objects, how do you learn grasping without getting into the mathematics of grasping, without finding form closure, force closure? How do you get into learning how to grasp an object? And these objects are of different types. For example, objects of daily living. And in the Amazon challenge, I think they won the 3rd prize that year. And every year there is some challenge or the other, and they're very active in that area, using machine learning and AI techniques for learning-based systems. We also look at industrial projects for using automation. Now, this is application of engine inspection. So for engines, especially trucks, when the truck has gone for about 10,000 or 20,000 kilometers, they need to inspect the engine. And the only way you can inspect the engine is to open the engine and then to look inside the piston, the cylinder, right? And this takes time and it's expensive. So what was done here is they devised an automatic method in which you have a probe, which is something similar to the laparoscopic probe. So we have a very small probe, and this probe, which contains a camera, okay, and has LEDs to provide light. This camera-based probe is inserted into one of the holes. So on the left side, you can see the engine is not open, but you can access it, okay, from the spark plug. So they can insert it there, and this automatic system can rotate and get the image of the inside of the piston. Now, based on this image, can you tell what is the state of the cylinder of the engine? So this means without opening an engine, can you do it in 5 minutes and tell what is the state of the engine of the car? Okay, so this is some kind of AI-based or machine learning-based application using computer vision. This has been sold, I think, to Tata Motors, and they are trying to use it in their truck business. Now, moving on to aerial robotics. So IIT Kanpur is probably the only institute which has its own airstrip. So we have an airstrip where of 100-meter runway, and there are aircrafts which come here routinely, and we have our own aircrafts which have 6-seater aircrafts plus gliders. So the next time you come to IIT Kanpur, please do take a trip or visit our airstrip and take a joyride around Kanpur city. Okay. So in terms of aerial robotics, we have the aerial robotics, which is basically winged aircrafts. Then we have helicopters. Then there are a cross between helicopters and winged aircrafts. And the aerospace department, which is very big here, and they basically look at the complete range from design, simulation, modeling, then motion planning, vision-based control, okay, the full gamut of expertise in this area. And there is a very big lab for helicopters, especially because helicopter flight is supposed to be difficult to control compared to a winged aircraft. So these are some of the pictures. The left top is the airstrip, okay, and these are some of the robots which have been made at home, and some of them are for the defense forces, and others are for research in different areas of control, autopilot, motion planning. So these are some of the aircrafts which have been made, fixed-wing UAVs. Then we have tilt quadrotors, quadrotor convertible planes, and then conventional quadrotors, IC engine helicopter, then variable pitch quadrotors. Now this IC engine helicopter is something interesting, that they are not using electrical motor, but they're using an IC engine, okay, which is a small IC engine, the one that is used in motorbikes, or much smaller version of that, to fly the helicopter. And in terms of design, they have looked at various types of designs. For example, the VTOL concept. So there is also a company which is there, which is trying to build an actual VTOL aircraft. So this is the top one on the center is a compound helicopter. So there is a quadrotor convertiplane. Okay, so this is, you can see it has a helicopter rotor on the top, and it has blades in the front. So it is a compound helicopter. On the right is a quadrotor tail sitter, and then we have a quadrotor convertible plane, which can convert to a fixed wing. It can fly like a fixed wing aircraft, or it can fly like a quadrotor itself. So these are some of the research areas they're working on. SWARM architectures for communication between different kinds of aerial vehicles, helicopters, fixed-winged aircrafts. Some homegrown new kind of quadrotors. So engine-based quadrotor, where there is no body here. It is fixed straight to the quadrotor, and then you have a quadrotor which is an engine-based quadrotor. Okay, these are prototypes which have been made and tested. Then novelly fully actuated tilt augmented quadrotor helicopter. I'm not in this area, so I'm not very familiar with what this is, but what I understand is you can tilt the quadrotor and then it can behave like a helicopter if required. The other area where we have been working on is micro-robotics. So at the micro scale, you need to make devices. So there is the National Center for Flexible Electronics, where they make micro devices, sensors, small robots at the micro scale using flexible electronics, printed electronics. And we are also working at the micro scale, where we can make very small devices, very small linkages for robots and users. For example, making micro holes, making micro sensors, which are used in robotics applications. So I think my time is up, so I will stop here. So thank you for your attention. Yeah, so I was the last speaker, so I thank myself.
Yes, I did. Thank you.
Okay, so I will stop sharing. We can have a very short discussion. I think we had a long morning and a long afternoon. So we can have a very short discussion and then we can end the workshop session today. So at the very beginning, I'd like to echo what Yamazaki sensei said today morning, that he was not very sure of what is the objective of this workshop. Okay. So I will echo and say that I was also not very sure what is the objective of this workshop. I think none of us were sure. Okay, but as there is an old proverb that a long journey begins with a single step. So I think this is the first single step, that at least we know that you're there and we are there, and we can have some kind of a long journey onward, right? Shibata, what do you say? So,
yes. So yeah, I totally agree with you. Thank you very much. So this is, I actually learned a lot from your presentations, even from Japanese presentations. So yeah, so we'll be able to develop. So yeah, from now on, yeah. So we'll have. I think we'll have this kind of workshops. At least once in a year, and maybe more, and always need to consider. So let's consider to develop actual collaboration. I mean, human resource exchange, or start getting some grants together, or develop some grants together. For example, JST, DST grant, and also some yeah. So let's start personal contact also. Yeah, and thank you very much. I'm really happy to be here. Thank you very much.
Yeah. So if anybody would like to share their views as to the way forward. Yeah.
Yeah.
John,
can I speak?
Yeah. Who is it?
Ashokan.
Yeah.
Yeah. So thanks to all the speakers for all those presentations, and it was very interesting to know about the type of work going on different places. As Shibata mentioned, we may not be knowing what is the work going on in our own place or nearby places. So this kind of workshop helps us to understand the diversity of work, research work going on. So it was it was nice to attend and listen to all the speakers. So as you know, this the proposal for this workshop actually came during our GBM, the body meeting, and Professor Shibata agreed to coordinate from the Japan side to have a workshop, which will be the first step towards a better collaboration with Japanese researchers, maybe between TRS and RSJ in the beginning, and then we can actually expand it to other universities and other faculty also. So we can actually start discussing with individual faculty. So I found that there are many people who have common interests. So we can start individual discussions and then see how that can actually be taken up as either a big project or through some individual collaborations. But in any case, we need to keep the momentum on and then try to see how best we can utilize this to take it forward for better collaboration with India and Japan. Once again, I thank all the speakers and all the participants for attending this. Thank you.
So, thank you. So, Professor Joante Venture, Professor Joante.
Yes, I really wanted. Can you hear me?
Yes.
Yes.
Okay, good. Okay. So I really wanted to thank you for the opportunity. I was a little bit like Kimitoshi at the beginning. I wasn't sure about what would be like what we'll be discussing and how things will turn out for the workshop. I am super happy we had this workshop covering all the activities that you have. And to follow up on what Tom was saying, so there is this like GST, DST program, but there is also a GSPS, DST program that I was very lucky to have, and I did some collaboration with some Indian colleagues at NIT Rourkela. And there are multiple opportunities, but these are like opportunities between two researchers, one in Japan, one in India. But I think it would be really amazing, as also Tom said, if we could follow with a yearly workshop, either in coordination with an international conference or outside an international conference, just to continue the discussion, because so many of the presentations today were amazing, and there's so many things to discuss and to and so yeah, I'm super excited actually.
Thank
Yes.
you.
So thank you
Ashish.
actually, Venture Sensei, Professor Venture, so for organizing
Yeah,
the
we should
Japanese
thank
side
Professor
speakers. Thank you very much.
Joint Venture for the Japan side. I think we should thank her. I was waiting for the end to thank her, but I'm thanking her. I'll thank her again.
Yeah, Ashish.
Yeah,
Mr. Saha is, yeah.
Yeah. Well, thank you for this nice opportunity. And what I wanted to propose to the RSJ now to consider being a co-sponsor of this AIR series. So far, I think they are not supporting this thing officially. That is one thing I request RSJ to consider. Number one. Number two, in the list of their supported conference, then automatically, AIR will be visible. That is one from the RSJ side. The second is the collaboration. Of course, certainly, GSPS, DST. In fact, there was an attempt a few years ago, DST, GST, in the area of robotics, but actually it was the cyber security which has won the big grant from DST, JST. But certainly GSPS is another one, but those are mostly from the research. We may facilitate those activities, but I think co-sponsorship of this RSJ to AIR, that's number one. And number two, this annual workshop should continue. We have 1 year AIR and another year is a workshop. So this workshop should continue as we have done it today. Thank you.
Thank you, Professor Saha. Yes, I think technical sponsorship from RSJ, yes, I think that is something that we can work towards. Yeah, anybody else? Professor Yamazaki Sensei, would you like to say something?
Thank you very much. I'm happy if we have some collaboration. Yeah, thank you today. That's all.
Okay, thank you. Anybody else? Ekta
And so,
and
yeah, actually, this is all about first thank only for the entire all these speakers. And in fact, as I have already mentioned about our local ground here, the platform about Punch Robotics, the way our national society, that is Robotics Society of India, is helping us to uplift, because the way we'll be connected together at the national level. Now I'm sure that RSJ will be taking their help to uplift, because earlier, otherwise without these workshops, we'll always keep thinking, oh, maybe we don't know when we go to Japan and what is our targets to really step to incorporate. So I would say, like, why only after an annual? Because annual events are too far these days. Annual is like workshop or a conference. Anyway, we are doing. So these online thinking, of course, we could not enjoy the coffee from Kanpur today, but this online sessions have helped us that how by giving only half a day we can actually conduct more. So maybe if you can consider about little more such workshops, maybe at least in 6 months next, rather than waiting for 1 year.
yeah, okay, thank you.
Thank you.
So anybody else?
From the participant side, you may give an opportunity, other participants.
We have Q&A actually, basically.
Achha, okay.
So I think, no, there are no more questions.
Actually.
Okay. So I think we can end today then. So at the end, I would like to thank from the Japan side, Professor Yonte Venture, who has collaborated from RSJ side, Professor Tomohiro Shibata for the great idea of getting it started, and everybody else. So we are collaborating. RSJ does help. Professor Shibata manages to get us reviewers for our papers. So that is collaboration. Okay. And I also help him by reviewing some of his papers. So that is also collaboration. And yes, we should move towards having technical collaboration from RSJ and also having this workshop yearly, 6 monthly. Okay. One issue is that people wanted a conference. We also have something called the Asian Robotics Society. You might be aware of that. Okay. And there was a proposal to have an Asian robotics conference. Okay, through the Asian Robotics Society. But however, it was felt that there are too many conferences. Okay, people are running from here to there. There is conference every day. Okay, so maybe having another conference is not a good idea. So we should collaborate more. Okay, and look for this DST, JST kind of funding opportunities in the area of robotics, and also through informal meetings and collaborations. So thank you all very much today. So let us please do attend AIR. It's open to you all. The link is the same. So whenever you have time, please drop in. Okay, the AIR
Professor
conference
Datta,
is...
1 second. When to answer this? Because many people have not written. It was mentioned that we'll answer during the session, or is should I write here?
You can, yeah, you can write it
There's
now.
1 or 2 questions.
Yeah, there is one for you. So you can answer it now.
Yeah, so it was, I was about to write, then I thought probably it will be discussed. Anyway, the question is regarding the number of modules, how it will be decided for a particular task. And actually we work in 2 or 3 phases. In the first phase, we decide on the number of degrees of freedom, that is the optimal synthesis phase, in which based upon the task, which is actually the number of points and their orientation, so what position and orientation, you actually decide the optimal number of degrees of freedom along with the optimal values of pH parameters. So whatever is the number of degrees of freedom, that gives us the idea of the modules to begin with, and then at the later stage we just do some kind of validation also. So at the first stage we decide on kinematic, based upon kinematics only.
Okay, thank you.
There is one for Ashok.
Yeah, there is a question for me. So can the underwater robot which was presented initially be used for dragging a survivor to the shore? So this robot is not exactly for that purpose, because that is only a surface vehicle can do this kind of dragging a survivor to the shore. But salvaging an object from underwater, yes, we may be able to do it by properly attaching a manipulator arm to the vehicle. But otherwise, an underwater robot is not exactly for getting people out of water. That maybe we may have to have a surface vehicle and attach with its own arm or other attachment, and then can be used for dragging a survivor. That's my answer.
Okay, thank you. Then let's end the session today. So thank you, everybody. So I would say arigato gozaimashita until the next time.
Thank you very much.
Thank you, Ashik. Thank you all.
Thank you.
Bye all. Yeah.
Okay, bye.
See you in the.
Bye. Yeah.
You want to make that announcement?
There are participants are there, right? Yeah.
Yeah.
Okay, so the next announcement for the participants is that the next session will start at 2 o'clock. And 2 o'clock we have the session is machine learning applications in robotics using MATLAB. So it will be conducted by MATLAB. Okay, Mr. Dhruv Chandel from MATLAB will be conducting the workshop. She'll be talking about reinforcement learning applications in robotics, mainly focusing on reinforcement and what MATLAB facilities are there for reinforcement learning in robotics. Okay, so that will be from 2 to 3:30. Then we have a short break from 3:30 to 4. And from 4 o'clock to 6 o'clock, we have the tutorial by Professor Sunil Agrawal, Professor of Mechanical Engineering and Rehabilitation and Regenerative Medicine, Columbia University. And he'll be talking about design and control of rehabilitation robotics. So please do attend the workshops because they are very informative for students and also for us, okay, to know how things are around the world and how things are done. So let us take a break till 2 o'clock and we'll meet you around, say, 1:45 again. Okay, so thank you.
So we'll turn it off so that it goes to the networking area.
Yeah, we can do present off now.
Yeah.
Okay.